No, this is not an example of code hooking yet. This is how it looks then if you have a real call. You have a create file function in the application, which opens a file or creates a new file. Then in the kernel, in the user mode kernel wrapper, you have the jump in point for the API, which, as I've already explained, then first converts it to Unicode, and then calls create file W, which is the Unicode version of create file, which then calls ntdll that W create file, which means this is a native API, so to speak, which shouldn't be used as it's not consistent between different Windows versions. And in TDLL, you then have the setup of your jump to a kernel space. You set up some structures, path information, and then call the interrupt, or call this enter, depending on, as I've said, Windows and kernel, Windows and CPU version. And then in the NTOS kernel, actually, you have the software interrupt handler, which then has a really big table, which has a list of all the calls, and then does the actual work in step 4. And then, of course, you go all the chain back to the application. Now, how does CW Sandbox actually hook these codes? It's a very simple method called inline code overwriting. Normally, you have your normal jump create file hook. But what it does, it first executes that function, and then after executing the function, no, sorry, I'm wrong here. It jumps to the hooked code, which is overwritten. This jump gets overwritten by their code. Then there's a custom hook code, like, I want to preprocess this code, I want to log it or whatever, and then jumps to the saved stub. So what the stub, which is actually where the jump was, is saved somewhere else, and it then jumps there. And then in the saved stub, there's a setup to the actual call, which is happening there, and then it's actually calling the kernel in the end. So you just take the original code, put it somewhere else, take a jump to your code there, after that jump to the original code, hoping that it's position independent, and then continue execution as normally. So by API code hooking, code overwriting, and DLL injection, because all that overwriting takes place in a DLL, which is getting injected into the malware process, you can hook all the code of these API calls and then record them. And by doing that, you can, of course, seeing all kind of APIs for file access or whatever access. And you can record that information. And what I do with CW Sandbox is do that for 3 minutes, and then you have a huge list of just which functions were called with which parameters. They analyze it and convert it to XML, which is not so easy as it sounds, because you just have handle values and need to actually convert them to which files were accessed when, and you need to correlate time and whatever. But in the end, you get a nice fancy XML output, what has it done, and you can then further use it. So you have that CW Sandbox process in the virtual machine, which invokes the malware application or executes it, and forcefully injects the CW monitor DLL, which is doing the actual hooking into that process. That DLL is communicating by some pipe with the CW Sandbox. The CW Sandbox is doing the actual recording. And since we're doing code hooking here, we can also behave like a userland rootkit. So CW Sandbox can hide its own presence as it filters all APIs which could be used for detecting CW Sandbox presence. And also, since we are hooking all code, we can also hook the code to execute new files. And if the malware application, for instance, downloads a new binary and then executes it, we can also inject the CW monitor DLL automatically in the new binary. Nowadays, you often have downloaders just spread you have a really small binary, which is executed, downloads the real huge malware from the internet, and then execute that one. And this is really neat because you're seeing both depths, because there's no real command and control or whatever in the downloader. It's just fetching the file and executing it. But this way, you see both files. Yeah, that would be a demo now here, but on Black Hat, which I don't have here. Sorry, as I've said, not my slides for this Congress. And now, what we have achieved now is we know where the botnet command and control server is. We know how to communicate with that server. And now we want to see what's going on, which commands are issued actually, and so on and so on. We have some properties of botnets that we can use for us. First of all, a botnet cannot impose authentication that is not also encoded in the bot's binary. Why is that? If you would have some sort of authentication and you wouldn't have it in the bot, how would the bot join the botnet? I mean, the bot, if there's a password, the password must be somewhere in the bot. If there is some specific encryption key, it must be in the bot, whatever. So by looking at the bot's binary, we can obtain all information necessary to join the botnet. Then, usually, and we rely on that, commands are forwarded to all bots and not some selected single bots. So what this means is that if we're seeing what one bot is seeing, we're probably seeing what all bots are seeing. So we might not see some commands to some specific bots, but from our experience, and we've now been working on botnets since 3 years, there is seldomly commands issued to specific bots. So we assume we're seeing everything that is there. And then botnets are so large that there either isn't any replies of bots at all, because if you issue a single command and all your 1 million bots you have in your great big botnet would then report back whether the command was successful, you would be simply DDoSing yourself. So there's no channel back because you cannot do that. Botnets are usually too big to actually get any responses. And if they are still so small because they are just by some script kiddies or whatever, if there is like 5,000 bots, there's a high chance that at least 50 of these are just experiencing a ping timeout or are not, a normal Windows user which just plugs out the power, so they are not logged off the botnet and still there but not responding. And what this means is we don't need to respond to valid commands. We just try to appear as a silent, turned off bot, and so we can hide in the masses. So this means we can just join the botnet, listen to all commands, and log it, and that's it, without being detected, hopefully and probably. So how do we impersonate such a bot? The simplest method is just run the bot binary in CW Sandbox or in the honeypot or whatever, put a sniffer on the outside of this box at the network border, and just look at the traffic, what's happening. And this has some problems. First of all, if you are running the real bot software and somebody is issuing a DDoS command, you're pretty fucked up because you're participating in the DDoS, and there's a lot of legal implications. You can avoid that by clever rate limiting and whatever, but it's a lot of work you could just avoid. The second problem is what if the command and control goes over SSL? Then you need to write your own SSL code, so you have to do a man in the middle, and that's just a lot of work if you just do it from the outside. So it's the most realistic because it replies to the commands as it should, and it does what the herder expects, but it's also hard to use. So better we use just some existing software for the control protocol. Still today, a lot of botnets are IRC based, so IRC is a command and control protocol, and there's a lot of good IRC clients out there we could use. The problem there is, at some point it becomes really hard if you're having an IRC and tracking, like at times we were tracking 500 different botnets at a time, and you have an IRC with 500 open windows. Then either you have a big, huge list on paper which window in IRC is what botnet, or you're just lost because, with 500 tabs you cannot distinguish which server are you on, and it's just not usable. So even better is you implement your own generic bot emulation software, and we've done that. It's called BotSnoopD because we sniff on botnets, and it's a daemon. So what does it do? What does it do? It's a daemon dedicated to snoop different kinds of botnets. Like, as I've said, we have a lot of IRC botnets still today, but emerging is HTTP for command and control, so you have an HTTP server which is serving the commands, and they're continually fetching the file with the commands. And also what has been there only is peer-to-peer, so not file sharing, but peer-to-peer communication, so there's a really decentralized command and control protocol, like in the Nugashi botnet, which is interestingly not so hyped by the media because there's still about 200,000 hosts in that peer-to-peer botnet. But the problem is, since there has not been so much research on it, nobody knows how to take care of that peer-to-peer botnet because there's no central server you can take out, as we see later. And so, well, we live with that this botnet is still floating around and people just don't talk about it. So again, we realized that there might be a lot of need for extending this daemon, so we have again chosen a modular design, which is extensible via plugins or libraries. And we have developed our own daemon, since we're using all the network stuff in Nepenthes and shared in botsnapd for performance. So we're single-threaded using Paul and whatever, which is really fast. So we can have, we have at least 100 botnets on a single machine, but that single machine isn't one of our spare hardware. It's an 8 megahertz Duron with 256 megabytes of RAM. So with a good server, you can track more, but we haven't tried this. And yeah, it will be released under GPL when we're really confident with it. At the moment, well, it's stable, but not as stable as it could be, probably. So it's still in the work. A schematic overview is the most important thing is the client modules. We have one for client for ISC, one for HTTP, one for Nugashe. And these are just the implementations of the command and control protocol. So client ISC is just a simple ISC client, HTTP is a HTTP client, and Nugashe is a bit of more advanced because if you want to participate in a peer-to-peer network, for command and control, you cannot just connect to the central server and assume you're getting all commands, but you need to really participate in the peer-to-peer botnet. So you need to contact a node, and this one tells you, no, I'm full, please try these ones, and then you contact these, and then at some point you connect it to some amount of nodes, and then getting hopefully all these commands. Of course, there can be separated clusters of nodes with no connection in them. It's a usual properties of a peer-to-peer network, so it was a bit more work. Yeah, then we have added to that proxy modules you see on the left. So we have our networking core, which again transparently uses proxies because what we experienced in the past. There is some botnets where they find out that you're not a valid bot. Like for example, there's some botnets which just have 80 bots. And you think that's really small, and well, we don't care anyway, but these 80 bots are some really high bandwidth servers, so they might have the same bandwidth as an usual 5,000 botnet, but if you're having only 80 bots, it's really obvious if somebody pops in, doesn't reply to the commands, and so the pre-assumption with hiding in the masses does not work. So what we saw was there was a huge DDoS against us, and luckily we were on the dial-up IP, so we just dialed back in, and some other poor guy was then DDoS dialing in after us, but well, that wasn't our problem. So we've added proxy modules for SOCSphere or HTTP proxies, and now we have several volunteers who also have dial-up IPs, so we can spread on different IPs, and we don't need to redial in all the time. And we're not using public proxies because that would be really bad. You know, you would be seeing a lot of DDoS against public proxies if you would be using them otherwise. And you can go with SOCS4, you of course can go through the Tor network as well. Then we have emulation modules, which are invoked by the client modules, because we were not confident that we were kicked off that 80 bot botnet, so we added our emulation of generic IRC bots. Like if it says there's some, for example, in our bot there's .auth for authentication, and we then look at the first 5 results to that attempt, and either then say, okay, this key was okay or not, depending on what the others answer. So we don't need to hide in the masses at all anymore. And the other thing, the generic IRC, no, that was the RBOT one, but the generic IRC one reacts on commands like .j or .join, so we can join other channels on an IRC server, for example, if there are additional commands in other channels. We have added reaction modules. The SnordSam module, SnordSam is a project for distribution of Snort rules or no, not snort rules, like firewall blocking rules. So